So before we dive into code, it's useful to talk about a few of the other behaviors that trees have. Trees have actually less behavior than lists to some degree, because especially when they're in sets. But they have some maybe slightly more complex algorithms involved as well. Ones that are similar: size, empty, and clear. So the size, hey, you can either count as you go and then update that in every time you add or remove something from your list, or you can count when somebody asks for size and then you just traverse the whole tree and answer your question at that point of how big the tree is. The empty is much like the list, that if the root is null, the tree is empty, or you can also check the size if you keep that separately, but I think the best indicator is if the root's null or not. If it's not null, tree's not empty. Clearing a tree, again, follows the same sort of follow through. I can clear a tree simply by setting the root to be null. I would then also need to do size as 0 if I'm tracking size separately. Um, the same thought holds as did in lists, is if you're in a language like C, C++, where you have to manage your memory yourself, you probably should free up that memory. A good list, a good set, a good map, whatever, should free up memory when things are deleted out of it. If you're in Java, it's less important because of garbage collection. You just need to make sure you're not pointing to it anymore. So in an array list, you have to really be careful you null out some values so you're not pointing to it accidentally. But in a linked list, as soon as I null out the root, everything else is subject to garbage collection at that point. So it makes your life a little bit easier. You don't have to go through and clear everything at that point. So these three functions, not too bad. The contains function then, whether a list is contained, is pretty straightforward as well. We just follow our rule that the things that are bigger go to the left, the things that are smaller go to the right, and the ones that aren't are equal, right? So the biggest thing you have to remember is it is possible that the contains doesn't land on anything. You could get to the bottom of your tree and the value wasn't there. The tree doesn't necessarily need to keep every single possible value. So you have a short search feature, but it doesn't necessarily come up with an answer every single time. Removing the nodes can be pretty challenging. There's three specific cases you have to consider within removing the nodes. Now, the leaf nodes are pretty easy. If I find a leaf node where the left and the right are null, then they just, like number 2 right here, they just can be taken out. You just take it out by essentially returning back to the caller a null node at that point. You'll see inside of there. There's a really clever way of resetting it, which allows you to manage the root really nicely. And later on, we'll see it actually helps us to balance trees without having to dramatically change the interface as well. Now, the nodes with one edge aren't quite as easy. Now, so for instance, let's say I want to remove node with the value 5 right here. So this has a child right there, number 2. We don't want to lose number 2 when we replace this one. So we can actually just delete number 2, just to have that node go away. And what we do is return, since it only has one child, we return that child to become the new child that comes in. So the rule that you're going to see is inside of there is if the left node is null, return the right node. Else, if the right node is null, return the left node. The irony here is the same logic actually handles the leaf node as well. So if the left node is null, I return the right node, which is also null. It just amounts to deleting the node itself. The great thing about sets is, since I'm saying remove it by value, there's no indices, I never have to worry about returning anything. I just have to tell you whether or not I actually deleted something. So it makes our life a little bit easier. All right, so where it gets really tricky is when we have to remove a specific value that has both a left and a right children inside of there. So for instance, number 19 in this case. So when I'm going to go say remove number 19, I can't just delete it, because otherwise I would be orphaning out the 5 and 2 and the 21 and 20 as well. So what I need to do is I need to go essentially find the lowest value. I slide to the left again. So for my right subtree inside of here, I find the lowest value, which in this case is 20, and then I overwrite that value onto the existing node. So I'm not going to just drop the node in this case. I'm going to reuse the node, but I'm going to throw a new value in that node. I'm going to drop, specifically call, and go delete that other node at that point. Oops, excuse me. And then I return the same node involved. I'm sorry, I return the the node that I am, right? Yeah, exactly. The node that I'm out there. So I keep the same node in place. I'm just deleting something further down. Now, when I delete that further down, I'm actually doing a recursive call to delete that one further down, and it might bubble up through a whole lot of the tree. A bunch of the tree could potentially change inside of there. But the most important thing is I don't have to reestablish my left and right at that point in the same way. Now, you'll see this algorithm, you'll go work in this algorithm. The biggest thing that, and hey, I fell in this trap as well, is the other ones you're replacing the nodes. You're setting the nodes right. In this case, you're replacing the value. When the left and right are out there, we're going to keep the tree structure in place and just change it to the minimal value, and then separately go delete the other value. Again, which might cascade, but an important concept, an important thing to remember. So now's the time that you're really going to dive into this and go build the tree. If you kind of get stuck on the remove, remember this video is here. You can go back and look at it. If you really, really get stuck, as always, you can reach out and ask for some help. The concepts of these trees, like the linked list, aren't really super difficult, but building the code is super meticulous, and it's a little bit hard to see and picture it. So we're going to use videos like this and also some by hand examples to try and reinforce the idea of getting that perspective of a single node in time, of the recursive call to that, and stop looking at the whole structure and thinking, well, I know what to do because I can see the whole big picture. Of course you can. The trick is not being a really clever game player when you see all the moves in front of you. It's how well do you know when you can't see what the other player is doing, or in this case, you can't see past your children node, and you definitely don't know what happened before you. So that's going to be the trick in setting that perspective as you code these. So remember that and use these resources to help you be able to solve those problems as well.